Welcome you to this video. Here we today we actually discuss discrete random variable. So this is your chapter number 2, discrete random variable. Now before starting this, let's define definition. First definition of this chapter is about random variable. So what is random variable? So a random variable consists of an experiment with a probability measurement P defined on a sample space f and a function that assigns a real number to each outcome in the sample space. So the main idea about random variable is to actually assign the real number to the outcomes which have some probability. So it is known as random variable. Now we defined in this chapter, we discussed discrete random variable. So what is discrete random variable? Now discrete random variable, if a random variable x, we normally represent random variable with a capital letter. Here x is a random variable, is a discrete random variable if the range of x is a countable set. So discrete random variable is one where you have a countable set. So normally we represent sample space by S. For random variable we use subscript with the random variable. So this shows the sample space of the random variable which assigns real number. The outcome, for example, we have x1, x2. Now this is a countable set. So this set is known as discrete random variable. Next we look at another definition, and this is basically about finite random. So in finite random, x is a finite random variable if the range is a finite set. So what this means that if you have s of x but it is not infinite, In previous example we wrote the infinite, but here we have a finite range. Okay ji, now let's do an example, and example is 2.5. Now in this example, suppose we observe 3 calls at a telephone switch where voice call and data calls are equally likely. So we have an experiment which observes 3 calls. The sample space of these experiments based on voice and data calls. So either 3 are the voice calls, 1 is data, and they can have a different position when data and voice call are interchanged, or we have 2 data calls. Again, data call can be before the voice call, and the last one is 3 data calls. So there are 8 outcomes. Now question is, let x denote the number of voice calls, y the number of data calls, and let the derived random variable that is based on x and y. So if we want to look at how this random variable look like, so it's easy to make a table here. So assume that we have a table here. Now this table includes outcomes and probability. For example, we have 8 outcomes. So first outcome is assume that we have 3 data calls, and it says that these are equally likely, so in that case outcome is 1 by 8. Similarly, we have 2 data and voice call, again 1 by 8. Then we have DVT, again 1 by 8. Then we have VDD, again 1 by 8. Then we have DVV, again 1 by 8. Okay, then we have VDV, again 1 by 8. Then we have VVD, again 1 by 8. Then we have triples, again 1 by 8. Now let's look at x. X is the number of voice calls. So what is the number here? Voice call is 0. Here 1, 1, 1, 2, 2, 2, and 3. So this is the outcome that we get here. Now the next is let's what about y? Number of data calls: 3, 2, 2, 2, 1, 1, 1, and 0. What about r? R is multiplication of x and y. In that case, this becomes 0, and multiply 2, 2, 2, 2, 2, 2, and 0. So if I wrote here range of x random variable is 0, 1, and 2. Range of y is again 0, 1, and 2. Sorry, 3 is also there. Let me rub this. I forget the 3. So also 3 here. What about range of r? It is only 0 and 2. So these are random variables. So the idea is to assign the real number. Now let's do a quiz here. 2.1, and quiz says that a student has taken 2 courses. In each course the student will earn a B with probability 0.6 and a C with probability 0.4. Okay, so a student take 2 courses. Okay, so these are 2 courses, and for each course probability is given as for B grade is 0.6 and for C grade is 0. So if I wrote here, probability for C grade is 0.4, probability for B grade is 0.6. So a student takes 2 courses. Now to calculate the grade point average, B is worth 3, so B is equal to 3, and for GPA, and C is equal to 2 points. Now question is that the student GPA is the sum of the GPA for each course divided by 2. So GPA or you say that cumulative GPA is equal to GPA of course 1 plus GPA of course 2 divided by 2. This is the formula. Now question is, make a table of sample space of each experiment corresponding values of the student's GPA. Now student can take 2 courses, so either first course can they get B grade or get C grade in first course, or in second course if first is B grade, again he get B grade or he get C grade. Similarly for C he can get B grade and C grade. So if I look at the sample space first, so sample space has the outcomes like both B and C, C and B, and both C grade. So this is the sample space. Now the probability, if we, because if it get B grade probability is 0.6, if we get C grade is 0.4, again if we get B grade 0.6, C grade is 0.4, similarly here is 0.6 and 0.4. Now from here BB cumulative probability is 0.36, similarly BC cumulative probability is 0.24, again CB 0.24, again CC is 0.16. Now if I make the table, so let's make a table here. I call it as a probability values, call it here as the outcomes. Now we have BB as the outcome, we have BC as the outcome, we have CB as the outcome, and we have CC as a outcome. So there are 4 outcomes. For BB probability is 0.36, for BC is 0.24, 0.24, and CC is 0.16. Now GPA, so for GPA, which is actually the random variable, this is our random variable, and it says that for GPA you have to add the both probabilities and then divide by, add the points and then divide by 2. So GPA is a function. When you give BB, so means that GPA is a function. When you give an input B, what it did, it actually do 3 plus 3 divided by 2, so it becomes 3. If you give GPA BC, so it will do 3 plus 2 divided by 2, it becomes 2.5. Similarly, if you give CC, it will do 2 plus 2 divided by 2, that becomes 2. So just when BB, so we have 3 plus 3, 6 divided by 2, again 3. BC is 2.5, CB is again 2.5, and CC is 2. So this is the way you can write the random variables. Now we will move to next article is 2.2, and this article is about probability. Mass function. Now probability mass function, we also in shorthand write it PMF. So what is PMF? So we have a definition of 2.4. It says that the PMF of the discrete random variable is defined mathematically as P is for PMF, X represents the random variable, and small x is a particular range within the random variable, is equal to, you have to calculate the probability when capital X is equal to X. So this is the definition of a random variable. Now let's do an example to get the idea about this PMF. Example says that, now write the PMF of example 2.5. Okay, it says from example 2.5 that we did, what is the PMF of R? So if you remember, I go back, we did example 2.5 here. This is example 2.5 where we make this table and try to calculate the PMF. Now if you remember, R has a range and that includes two variables. If you remember, R is equal to X times Y, okay, and the range of R from that example was 0 and 2. Okay. So now when because PMF is defined based on the probability, so if you calculate the probability, for that it's better to make this table quickly. So these are outcomes, this is probability. Now if you remember, we have 3 voice data, then we have voice data voice, then we have data voice, then we have voice to data, then we have data voice data, then we have 2 data and voice, then we have 3 data and voice. So these are 8 outcomes. Now probability is 1 by 8 if you remember. If I do it very quickly so that we can able to solve this problem. And if you remember XY, X is the number of voice calls, 3, 2, 2, 2, 1, 1, 1, 0, and Y is number of data calls, 0, 1, 1, 1, 2, 2, 2, and 3. Now R is multiplication of X and Y. In that case, it becomes 0, 2, 2, 2, 2, 2, 2, and 0. Now, now we have to, I will use this space to solve this problem. Now we have to calculate PMF of R, small r. Okay. So this I need to calculate. So I have I know the range of odd that has 0 and 1, so I have to calculate probability of for 0, which is equal to probability when capital R is equal to 0. Now if you look at table, for 0 we have two outcomes, VV and DD. So this is equal to probability of 3 V's plus probability of 3 data points. Now in that case this becomes 1 by 8 plus 1 by 8, that becomes 2 by 8, that is 1 by 4, or 0. Now similarly we have to calculate PR of 2, that is equal to probability when capital R is equal to 2. So this includes all these terms, that is VV, VVD and so on. So how many we have? 1, 2, 3, 4, 5, 6. So this is equal to 6 divided by 8. That becomes 3 by 4. So this is what we calculate from here. Now if I go to next, so we have two values here. One is PR of 0 is 1 by 4, and the second one is PR of 2 is equal to 3 by 4. Now there are two ways of representing this. One is graphical representation and other is mathematical representation. In graphical representation you have y-axis that is represented by EMF, okay, and you have x-axis that is represented by a range of R here. Okay. Now for example it can be -1, can be 0, can be 1, can be 2, can be 3. Now you have to look at when R is equal to 0, what is DMF? 1 by 4, so you have to draw here 1 by 4, okay. When R is 0, 1 is 0, so only define it 3 by 4, so it is something like this, 3 by 4. Now if you add all these, magnitude must be equal to 1. Now mathematically we can write it as PR of R, and we wrote when PMF 1 by 4 probability here when R is equal to 0, then 3 by 4 when R is equal to 2, and what about other values of R? 0, other ones. So this is the way of representing the PMF. Now let's do a theorem here. Now is theorem 2.1. Now 2.1 says that for a discrete random variable x with PMF px of x, and we have range is s of x. Okay. Now first part of this theorem says that for any x, for all x, or it's better to write for any instead of for all. So it's better to write for any x, for any x, PMF is greater than or equal to 0. It will actually satisfy the axioms of probability as well. And the second part of this theorem says that if you take the sum that start x belongs to range of x, okay, so if I take, you take all the ranges, in that case this is equal to 1. Now the third part of this theorem says that for any event B, which is actually a subset of range, so the probability the probability that x is in the set B is, so this is equal to probability of B is equal to take the summation for all those outcome ranges which are belongs to B and calculate the PMF and sum all those, you get the probability. So these are three axioms that use for PMF. Now we come to quiz 2.2, and this quiz says the random variable M has PMF. Okay, PMF is given to us. Let me rewrite this thing. So is equal to C divided by N, and N is start from 1, 2 and 3, 0 otherwise. Now question is find, first one is the value of the constant C. So this is the first question. Now we will refer the answer, how we solve this. We will refer to the theorem 2.1, which says that theorem 2.1 part B, which says that summation x belongs to Sx, dx of x is equal to 1. We use this. So when we apply this, we can say that okay, summation n belongs to S of n, Pn of n equal to 1. So there are 3 points. So and this implies that summation of n from 1 to 3, Pn of n is equal to 1. When we do that, this come out to be C divided by 1 plus C divided by 2 plus C divided by 3 is equal to 1. When we solve this one, taking the LCM, so it becomes, this implies that it becomes, if I take C out and take the LCM, 6, so we have 6 plus 3 plus 2 equal to 1, so it becomes 11 on top, so C becomes 6 by 11. So this is the solution of the first part. Now we move to the next part. It says calculate, find probability capital N is equal to 1. Now for this one, now we use again definition, okay, of PMF, and using that definition, n is equal to 1 means that this is PMF of n of 1. So in case of 1, it becomes C by 1, that is, we know the value of C is 6 by 11, so it becomes 6 divided by 11. Okay. Now let's do the next one, part 3. Okay, so part 3 says that probability n is greater than or equal to 2. So for that n is greater than or equal to 2, so it involves probability of n is equal to 2 plus probability n is equal to 3 plus probability n is greater than 3. So as we know that from the definition that a value is greater than 3 is 0, so this part becomes 0. We left with these two. N is 2 means c divided by 2 plus n 3 means c divided by 3. Now if I take the c out, this becomes 5 by 6 multiplied by c. So we know the value of c is 6 by 11, so 6 by 11 times 5 by 6, it becomes 5 by 11. Now we move to next question. Okay, the next question is question number 4. It says calculate the probability n is greater than 3. Okay, for greater than 3, I told you that there is no probability is defined, so in that case this is 0. Now this is what we did to discuss the PMF. Now the next thing that we will start is families of 2.3 is actually families of discrete random variables. So we will discuss few families. So first one that we consider is definition 2.5. So this is known as Bernoulli. Random variable. So it is defined as you have 1 minus p probability when x equal to 0 and x equal to 1 is p, of course otherwise is 0. So this is Bernoulli, but the main idea here is p must be within 0 and 1. So this is Bernoulli. So we can look at example here. Example is 2.10. Example says if there is a 0.2 probability of a reject. Now in that case, so this means that p is equal to 2. So we have px of x equal to 0.8, 0.2, x equal to 0, x equal to 1, 0 otherwise. Now if we plot the PMF, so x0 is 0.8, assume this is 0.8 and x1 is 0.2. So this is PMF in Bernoulli case, so it is based on two possible acceptance or rejection. Now the next one is definition 2.6 is geometric p random variable. For geometric, x is a geometric p random variable if the PMF of x has the form x minus 1 and x is from 1 to 3 and so on. 0 otherwise. So for example, if you have a geometric series and if there is a probability of rejection, example is 2.12, if there is a 0.2 probability of reject, in that case px of x is equal to 0.2 times 0.8 power x minus y, that's x minus 1, and x is from 1 to so 0 otherwise. Now here if I plot it, so it starts from 0.2 then it starts decaying. And so this is the geometric series. Now the next one is definition 2.7, and this is binomial NP, random variable. Now for binomial random variable, we have PMF written as nx times probability of x and 1 minus probability of 1 minus x. Okay. Now we have example here. This is 2.14, and example says that if there is a 0.2 probability of a reject, and we perform 10 tests. In that case, pk of small k equal to 10 10k, and that is equal to 0.2 power k and 0.8 power 10 minus k. Okay, if I draw the PMF for this one, this PMF look like something like this. So if this is small k. Okay. Now we move to next one, is Pascal 2.8, Pascal KP random variable. So for this random variable, BMF defined as px of x minus 1, k minus 1. and we have p power k times 1 minus p power n minus x. So this is the Pascal one. So next definition, this next random variable is very famous one, is known as discrete. Uniform means that we have k and l random variables. So now for discrete uniform random variable, the main idea is that the outcome is equally likely in this experiment, and it is represented by 1 divided by l minus k plus 1 when x is start from k, then k plus 1, so on up to r. So otherwise is 0. Now let's do an example for this one quickly. The example is 2.18, and example says that roll a Faraday. So and the random variable n is the number of, so we define the random variable n is equal to number of dots facing up. So what is range of n in that case, because there are 6 sides, so 6 dots normally. This is the range. Now what is the PMF? So for PMF is easily written as, because it will likely so it becomes 1 by 6, 0 otherwise, and this is 1 by 6 for n is equal to 1, 2, 3, 4, 5 and 6. So if I plot it, so plot they have the same magnitude. One, 2, 3, 4, 5 and 6 with same magnitude. Okay, all is 1 by 6. Okay, the last one definition is 2.10, and this is Poisson random alpha random variable, Poisson random variable. So the PMF look like alpha power x and exponential minus 8 divided by x factorial. X is from 0, 1, 2 and so on, and we have 0 otherwise. So but there's one condition, that alpha must be greater than 0. Okay. Now let's do an example here. Example 2.19, and it says that we have the number of hits at a website in any time interval in a Poisson random variable. A particular site has on average lambda is on average hit per second, so there are 2 hits per second. And he says what is the probability that there are no hits in an interval of, so we have to calculate the probability there is no hit in interval of 0.25 seconds. So we have to find the probability. Now what is the probability that no more than 1 hit? Okay, now first of all we have to calculate alpha, that it give us the number of hits per second. So the time is 0.2, then we have to multiply lambda times t, that equals 2 times 0.25, that becomes 0.5x. Now after that we have to define the hit ratio using Poisson. so it becomes 0.5, okay, power h, and exponential minus 0.5 h factorial, and h is from 0, 1, 2 and so on, and 0 otherwise. So this is the way you can calculate it. So I will stop here, and in next video we will continue further on this. Thank you.